So, hello again, everybody, and we stopped with the model of the QAM-16 modulation. Do you have any problems, any questions? Is anything working so far?
For me, it's fine. It runs and everything is okay. So yeah.
So good. I will try to upload these videos today. Yes, so because I still haven't made any text guidelines, so this video will be quite useful for you, and you can follow them step by step. Hopefully, if you run into any problems, you can always type me email with problem, maybe send your code at once so I can run it also, and then I will be able to help you. So let us continue then. What we did now is made the channel model. This is actually discrete channel model because we are not converting our pulses represented by +3, -3, and so forth. I don't know, like +1, +3, into some waveforms as we regularly do. Yes, regularly we should convert this into some carrier wave with some specific phase, amplitude, and so forth. That would be continuous signal, and only then we add to the signal noise. However, in this particular case, you have seen that we actually add noise directly here. Yes, not here. This is much simpler simulation, require much less resources, and it works just the same. Yes, so in fact, today we also tried discrete time channel models. Now, what we want to do is to add filtering to simulate the band limited effect of the channel. That is one purpose, and the second purpose is to see how the structure of double RRC filters actually works, because previously in the first practical exercise we only made a raised cosine filter, yes, and that was it. And basically we compared how it works with some other type of filters which has no linear phase, whether are there distortions or not. But in reality, we usually split this filter in two parts. So we have this part of the transmitter, and we have part of the receiver. And each of them has square root of the RC filter. So that after multiplying these two filters, that will produce the complete root, raised cosine filter, right? So today we are going to try and see what happens if we look how signal looks after the first filter and after the second filter. Because, as you remember from lecture, let me remind you fast, the square root filter actually allows intersymbol interference. As you can see here, it's not always zeros. Yes, well, here it starts to become zero, but clearly here we can see it's not a zero. And for red and blue, here also is not a zero, which leads to intersymbol interference. Yes, and what we want to see is how this intersymbol interference can affect our received signal constellation. Let me take it, for example, for 10 decibel. So will the shape of these clouds change because of this interference or not? That is the question. It's probably obvious that the number of errors because of this symbol interference should be greater. It should increase. But we'll see if it is the case. Before we go further, let us actually make some changes to this code. First of all, I'd like to draw bare plot. Yes, so bare plot describes the error probability depending on the signal to noise ratio. Of course, you could run the script by manually changing SNR to 5, 6, 7, 8, and so forth, but it is also possible to automate this process and draw the plot automatically. So let us do this right now. So we specify that SNR is now going to be a range rather than particular value. We'll start from 0, we'll go with step of 0.5 and we'll finish at, well, at 10, for example. Let it be then, yes. Yes, that's correct. 10 is maximum value, what I was expecting to do. And now we need to actually make the loop. Yes, the loop with according procedure. So what doesn't change depending on SNR? Depending on SNR, generation of this data will not change because we don't have any noise effect on this generation, and these don't go through channel just yet. The map will also be the same. Transmitted signal is the signal without noise. Yes, original signal. So far, this doesn't affect anything. So where we can have effect is here when we add noise. So this part will go into the for loop. So I'm going to shift it with tab by one position and make a for loop. For, let us choose some variable, for example, k, from 1 to length of SNR. We're going to do all of these procedures. Let us add some text information that we are actually now processing specific SNR value, because this, if we increase the number of points, this can take longer, yes, and we'd like to be updated whether our program is working or it's frozen, yes. So just some short information. Its syntax is the same as for the printf function in C programming language. So I'm going to output float number here, decibels, and start a new line, right? And as a float number, I'm going to use SNR value at moment k. Yes. Specifically, I need to do same here, because otherwise it will try to take all the vector, whereas I need to take only specific values for each operation. So for 0, 0.5, 1, and so forth. Okay, this will work exactly the same. And also I want to keep all the values of the error probability. Yes. No need to output them here. Wait a minute. So this is not the error probability. This is the number of errors, yes? In order to get estimation of the probability, I need to divide with the number of total symbols, yes? So this way it will be error probability, symbol error probability, yes? It's not binary error probability, it's symbol error probability. As a number of errors related to number of symbols. Okay, so now each iteration of this for loop is going to save its specific value. Then it will plot the diagram for the highest possible SNR, which is fine. We don't want to really plot for each of these. Yes, it will be. Okay, now I need to end this for loop. And let's see how it works. If it works correctly, then we'll just display. It already processed all the data. That was quite fast. So if we look at error probability array, then we'll see that error probability decreases as the SNR increases. So SNR 0 represents this error probability, which is the worst possible solution case, that meaning that we have complete chaos and complete uncertainty if there is an error or no. And here is obviously the lowest error probability at 10 decibel. Now we can plot this as the figure, yes, and let us do so. So basically we are going to start figure 2, and for plotting error probability, I think we should use Yes, because usually error probability is drawn like somehow like this, where we have here logarithm of the error probability rather than error probability itself. So we need to use logarithmical scale for y-axis. For y-axis, logarithmical scale is produced by using semi-log y function. So semi-log y function. This is, roughly speaking, this is almost the same as using plot x log y, basically. However, it just does automatically this logarithm calculation for us, so it's more transparent and easier to see the logic what we are going to do. So x-axis is going to display signal to noise ratio vector, all the values from 0 to 10, and accordingly y-axis is going to show error probability values from the first to the last. Yes, grid on, some labels, x label S and R in decibels, and y able is symbol error rate, SR. We can draw this and see the plot. So this is how this noise immunity curve should look like for quadrature amplitude modulation, roughly. We can, of course, compare to see Google QAM-16 symbol error rate, if it is similar to what is expected to be or not. Yes, for example, here we can see that for 10 decibel we could be around minus 1.5 or something like that. Well, -2, -1.5. Yes, there may be some differences in our simulations, yes, but roughly here we have like 0. Wait a minute, 0.1. And here we should have 0.01. No, we have better noise immunity than in this simulation. Again, it's not really clear whether it is our fault or not. We also did use gamma parameter. I'm not sure they used this attenuation gamma parameter. Therefore, our noise is weaker. Yes. And so, but overall, the curve looks familiar. Yes, similar at least. Let us see this one. Yes, so here we have other. Yes, it depends on parameters. Yes, it depends on different parameters as well. And well, basically, care must be taken when comparing with other sources. Yes, for example, here we also have different values. Yes, quite difficult to compare actually. So 16 CAM is a red line. Here it has -3. Yes. At any rate, this depends on how noise is calculated. Since we here used built-in function AVGN, we don't really have much control over how this noise is calculated. It would be, of course, much better if we take things into our own hand and calculate noise dispersion variance manually. But this is already quite big practical exercise, and it will become even harder if we calculate noise ourselves. So we used this AVGN function. Of course, we can see more help on this AVGN, help AVGN, for some parameters, how the value of signal is evaluated, yes. So by default, it's assumed to have decibels. We can set it to linear as well. And we can also specify power. Yes, if we know power of our signal, we can mention it here. Also, we can say measured. Well, it's default. It's default. It automatically measures the power, and if it does so incorrectly, which can happen for discrete signal, then we need to calculate this power ourselves. But we will not do it so far. What matters the most is that conceptually it works correctly. Yes, the higher error probability for the lower signal-to-noise ratio. So what we are going to do now is to actually separate this part of the code in a separate script. So I'm going to make a separate script where I will pass all this code. I'm not going to do any clear here and say that this is the sim no filter. Yes, no filter simulation. So I don't do any filtering in this simulation. And call it here. So that would be task 1. Yes, it is task 1. Simulation without band limiting filters. Sim no FLT. As you imagine now, I will make copy of this file and add filtering in this. So basically what I will want is to actually have multiple simulations with filters, with one filter, with two filters, and without filters, and display all the plots at the same time. So for that reason, I'm going to well, actually, I'm not going to do anything in this code. It's already good. It's working and working as we wanted. What we need to do now is to calculate the filter. Yes, so according to this document, you can see what expression has been used in that script I have provided in Octal. And accordingly, what we are going to calculate is this RRC filter, part of the raised cosine filter, of this filter which we have studied in our practical exercise number 1. So the script is already finished, yes, and all you need to do is specify your own parameters. So let us see it. This sample rate actually can be calculated by us. Yes, so maybe let us do it. Let us do it. I'm not sure it is used anywhere. It is used here in plots when we display filter response. So we need to calculate it. However, in your particular case, we have quite opposite. Yes, so we know symbol time interval. Let us I think it should be already specified. It is already specified. We will call this script. So here, task 2, calculate root raised cosine filter. Yes. And we are going to call this script sqrt RRC calc automatically. So this program will launch this program, right? So it should have access to all these variables already. We don't need to really specify it in there. And symbol rate is going to be 1 divided by t symbol. Then samples per symbol is actually going to be here. Well, it's not really necessary. Let's see what was the original formula. So actually what we are going to do now is, rather than specifying 11 directly here, we are going to calculate a sampling rate, calculate symbol rate, and calculate it according to original formula. So it should match your specified value. Yes, so let's see the original code. How was it looking? So sampling rate divided by symbol rate. Yes. Fs divided by Rs. The sample rate is going to be n SMP times greater than symbol rate. So that would be n SMP divided by t symbol. Accordingly, if we divide these two values, then all that is left is NSMP here, yes, and automatically we achieve what we want. Next step, we need to specify bandwidth factor. Bandwidth factor in our code is called beta parameter. So let us write here beta, like this. And then we need to specify duration of the impulse response. So basically, if we remember our lecture, we need to know how many impulses we have. So we have here 1, 2, 3, 4, 5, 6, and so forth. And similarly, we have here. So this parameter is specified for you, like this, and sim. Yes. So for example, in my case, it is 5. So that means that I have also 5 here. Yes. So that is total of 10. Yes. And that's why here we have 8. So we replace this 8 with n sim multiplied by 2. And it's multiplied with this sample per symbol. We could replace it with NSMP according to our code, but it's not really necessary, right? This code will work as it works. Then here we have normalizing and plot response of the square root filter and full filter. So this full RC filter response should look exactly the same as it was from the first practical exercise. Yes, these plots are already working in figure 3 and figure 4, so they won't interfere with figures we had previously. So let's see how it will work. Do we have any errors or something needs to be changed? No, it looks like it's working correctly. Yes. So here you can see our filter impulse response of the full raised cosine filter. Raised cosine. Yes. And at the sampling times, simple times, it has exactly zeros. For root raised cosine filter, wait a minute, why is it so long? So here we have 67, and here we have more than twice as much. Something is wrong here. Is, in my case, it's 10. So let's check it. Ash pulse. Ah, wait a minute. I understand now. So first plot is actually square root filter. So let us increase it. Yes, you can clearly see that it's not exactly 0. Let us zoom it. Yes, here we have small, but not really 0 value. Yes, whereas here on the second plot, it should be perfectly 0. Yes, as you can see, it is a perfect 0. And this plot is twice as long because we calculated the convolution. So here, instead of calculating this filter according to the formula given in lecture, yes, which was given here, instead of that, we calculated the total filter response, which consists of 2 parts. So basically, where is that here? Yes, we calculated this response by connecting in series 2 filters. In that case, if this filter has response H1 and this filter has response H2, the total response H is going to be a convolution of H1 and H2. This formula is in fact provided here. Yes, it's integral multiplication in frequency domain. And since the filters are exactly the same, this multiplication H1 by H2 is actually H squared. So That's basically how it's done here. And in MATLAB code here, we did this by calculating this convolution between hash poles and hash poles, then normalizing it and plotting. Yes. So this hash, yes, is the total filter response. So what we are going to do now is to use our hash poles filter to simulate operation with one filter. Yes, so square root filter. Now there is one thing we need to be aware of. What we need to be aware of is that our quadrature amplitude modulated data, QAM-16, is happening at these positions. Right? So 1, 2, 3, 4, 5. Was it 5 samples per symbol for me? 7. 7. Ah, yes, it is 1, 2, 3, 4, 5, 6, 7. Or no, wait a minute, something little bit amiss here. Something a little bit not correct. So tabs, okay, singularity. Symbol time. Ah, wait a minute. Is this ST the same? Five doesn't really look like it should. But okay, I think that shouldn't be much of a problem for us right now. Let's go further and add this filter. So as I said, I'm going to make a copy of this file and save it. If I save file as sim RRC. We already have calculated this filter and its response is stored in hash poles, right? Yes, well, actually I interrupted myself a little bit when I was explaining what we should do. So the thing is that we need to actually fill in with zeros these missing points. So here we have data, here we have data. Wait a minute, I'm still confused. Maybe it shouldn't be like this point, maybe with that second plot is everything was okay. Let's check this plot, because this is where it matters. It has to be 7 samples before 0. So here we have maximum 1, 2, 3, 4, 5, 6, 7. Yes, it is 7 samples per symbol. It's okay. It doesn't have to be 7 samples to get a minimum in that plot. Yes, in this plot. It's okay that here we have these 1, 2, 3, 4, 5, 6, 7 here. Yes, this is where our data symbol will happen. And as you can see, it clearly will provide some inter-symbol interference. It depends on filter parameters too. Yes, but as you can see here, yes, this is what is expected from square root cosine filter. Yes, these oscillations can and are happening at these sample times. So everything is fine, no problems here. And as I said, in order to avoid sending data with these strong interfering points, which was better to show here, yes, we have to actually make sure that during these moments we are sending 0. So 0, 0, 0, 0, 0, 0. And here we have data, then 0, 0, 0, 0 data. Yes, so once per 7 symbols, we have sent one data sample and accordingly, well, 7 minus 1, 6 zeros, right? So we need to introduce these zeros first before filtering. Otherwise, we will, how to say it, distort our signal irreversibly and we'll lose data. So this part will remain. Yes, it will still do the same detection, still same error counting, but we also need to introduce filtering. So here we are going to add RRC filtering for the X part. So far we are working with transmitter. Yes, our receiving starts here with adding noise. And, we still haven't gotten there, so we are still working with transmitting part. Here we are going to introduce these missing zeros, right, by using so-called Kronecker multiplication. So how does Kronecker multiplication work? If we'd like, for example, if we have, for example, well, let us say some array 1 to 10, and what we'd like to do is instead of this array have, let us say, 5 zeros in between these points, so that we have 1, 5 zeros, 2, 5 zeros, and so forth. We can use this Kronecker multiplication by multiplying this entire matrix with Kronecker multiplication, not the regular multiplication, with the vector 1 and 5 zeros. So this way it will take the first value, multiply it with entire vector, and replace this one value with this multiplication result. In MATLAB, this is performed by cron operation. So first variable is our original data array or vector. Second value is this some kind of mask what we want to apply. Yes. And as a result of this Kronecker multiplication, we have exactly what we need. In our particular case, we need to add as much zeros as is specified by your samples per symbol parameter, yes? Except for one, yes? Because of these 7 samples, one of them is actually a symbol, and the other 6 are zeros. So, let us interpolate. So this procedure is called data interpolation with zeros. Yes, so let us perform this interpolation, data interp. I'm calculating this Kronecker multiplication for transmitted data and array consisting of 1 and zeros. We need to set here a row of zeros consisting of NSMP minus 1 zeros. Let me actually check if this will be correct. Yes, I have 1 and 6 zeros. Yes, you will have 1 and more zeros depending on what is your NSMP parameter. Okay, then. This is now interpolated data. And we are going to send, as you imagine, now 7 times more data than we need. However, don't be alarmed. We are not really going to use this distance calculation for all of this data, because as you imagine, our real data, what we want to read and use, are located at specific points. Everything that is between can be and should be simply erased, skipped, yes? So that means that before we are going to demodulate data, we are going to have skip all the unnecessary samples. Yes, it's going to happen here before this rip map operation. So we can already prepare place for that here. Here we are going to, how to say it, downsample. Yes, if this is called upsampling or interpolate with zeros. So now we're going to downsample 0 samples. Well, they won't be zeros because after passing through channel, because of inter-symbol interference, something will happen to them, but there should be zeros. We know that for certain because that's what we did here. We actually added these zeros which have no information, and therefore they can be safely skipped. Yes, and that's what we are going to do here. But before we can do that, we need to actually know how to correctly read our signal, because the filtering procedure will introduce a delay. Yes, as you can see here, before our data is read, we will have some time to wait, because filter has to calculate the output value depending on input values, and it will require a filter to fill in its entire memory. That will take specific number of intervals. We already talked about that on our last practical exercise. This is symmetric impulse response. Symmetric, yes. That means that this maximum is located exactly at the middle of this. And furthermore, here we have number of symbols and samples, yes. So basically n SMP multiplied with n symbol. And this will be +1 position. So our filtering delay will be this expression. Yes. Let us write it in here. So filter delay is going to be n SMP multiplied with n symbol +1. That is the first value we are going to read. Yes, and then each of the next values will be NSMP samples later. So if we return here, I'm sorry, this, wait a minute, this, no, was it this plot? It was this plot. So the next sample we are going to read is going to happen after NSMP values. The next one after NSMP more values, and so forth, yes? So the step will be NSMP, the initial value will be NSMP and sim +1, and all the other values can be removed. But okay. But we haven't made the filtering itself. Yes, we only calculated, prepare data by interpolating it and calculated introduced filter delay. Yes, so filter delay. Let us apply this filtering. Apply RRC filtering to interpolated data. It is performed by simple function filter, which we already discussed on our practical exercise number 1. At least I think we did. Let me actually fast check our practical exercise 1. So frec UZ, zeros, round, filter. Here it is, yes? So it happens exactly the same way. Input parameter, input signal is specified first, then filter impulse response. Wait a minute, sorry, no. Filter parameters first, then input signal, and the result is output signal. Yes. So our current input parameters are ash pulse, and this one is automatically 1 because we have finite impulse response filter, yes, which has no denominator in its transfer function. So we are going to perform filtering likewise here. Filter data filter is going to be filter ash pulse. No, wait a minute. How is it called actually? Let's double check because it's important to use correct name of the variable. So this is calculate filter ash pulse. This one, yes, okay. So it's small letter. 1, and input signal is data interpolated. Okay, so now we have performed this filtering, and we know where we should start reading our data. Therefore, wait a minute, just one more moment. Now, since we have done some modifications to our transmitted signal, we need to replace it here with data filtered, yes, before we go further. Actually, we can already try and see what happens if we work with this. So, run. Wait a minute, we cannot run this program. We need to run main program, yes, which we'll call then task 3. Simulation with one RRC filter. I'm sorry. Filter. Yes. And we are going to call the file sim_rrc. Now it will run first no filter simulation, then calculate the filter, and then run simulation with one filter. Actually, what I want is not to lose existing results. So here I'm going to add hold on. Here I'm going to add hold off. Also, I want to plot this part in different plots. So, how to say it? So, for example, I'm going to have 3 plots here, like this, with CAM constellations. So, no filters, RRC X1 and RRC X2. So for that reason, I am going to use a subplot command here. So this is going to be plot in subplot. There will be total of 3 plots in one row. So 1 row, 3 columns, and this is going to be the second plot. Similarly, I'm going to add to no filter the same thing, and this is going to be the first plot. Yes. So this way now I will have them side by side for different simulation scenarios, and I won't have to repeat simulation multiple times. Okay. Okay. Let me close everything. Something happened. Actually, I also want to replace title, so this is going to be RRC X1, meaning we have one filter RRC. Yes, here we are going to say we have no FLT, and I think I had some error. Yes, here we get technical. I didn't put the bracket. Yes, so I need to close this bracket. I started for cron, right? It highlights that according bracket that was closed. Okay, let's run again. Again, some error. Well, yes, it doesn't seem like it will work. Oh, wait a minute. And where is the first plot? So the first plot also wasn't drawn. And the error says the problem is in line 23, where we calculate the distance. Okay. So let's check what's the problem. Distance 23, distance here. Let's check if the problem is here. It shouldn't be Rx, it should be FLT, right? The wrong size of the vector. So, and either here we should have length of data FLT. Okay, now I think it should match. And at the same time, by the way, we want to keep the old PR, which has been calculated here, and this is going to be, for example, PR1. Accordingly, here we have plot PR1. Yes. So let's try again. Uh, 16. No, not working. Okay, let's see now. What's the problem? So we calculate data RX matrix by replicating it 16 times. So data RX matrix. Let's check it. However, it contains much more columns than it should. Okay, something is wrong with our filtered signal, maybe. Let's check it. Data filtered. Yes, it has 7 columns. It should be in 1 column. So something is... wait a minute. So here, when I was upsampling it with zeros, data transmitted wasn't a row, right? So data transmitted, first 100 values, is a column, and it did exactly what I asked. It replaced this value with entire row of 1 and zeros multiplied by this value. So that means that if I look at data filtered, yes, we have value, we have zeros. So that means that we need to actually generate these zeros in the column, not a row. So this means here we have semicolon and a colon. Well, actually we can just simply transpose this, yes, and it will convert into a column. Much simpler to do. So this will now run, or it won't. No, it doesn't work. Let's start again. Okay, now the problem is 29. Line 29. Counting the number of errors. Obviously, because we need to compare with data interpolated now. Yes. And we might try running this script now. It works. And now it will plot the results. So, as you can see, this is a complete mess here. Yes, because of this intersymbol interference. And if we watch the number of errors, PR1, it's always high. Yes. Or wait a minute. It's always the same, actually, even. But what is this number? What does this actually mean? Well, here actually we also need length data interp. We can recalculate this last value. Yes, error probability cannot be more than 1, right? So the error probability is 99%, right? This is unusable channel, and the bear or SER curve is also a constant here. So that means that this doesn't work, and there are many errors because of these zeros, which we didn't skip. Now we need to remove all those zeros by accordingly reading correct values. So as I said, the first value which we are going to use is going to be this filter delay value, and each of the next will be located at an SMP distance from that. So downsampling will be happening here. Let us calculate a new version of received signal like this. Yes, so this is going to be our existing received signal, starting with filter delay value, then step is an SMP, and up to the end, by the end, right? Then here we are going to use this data RX again, length of the data RX here. It's no longer n because we lose some of the values, right? But it's fine. And accordingly, symbol error probability also needs to consider data Rx here. So we skip these zeros and everything should look fine. Let's see. Now it's still simulating. Okay, now we cannot really compare because, as you can see, our demodulated data is no longer 100,000s, it's 9995. Yes, 5 values are missing. These are exactly those 5 symbols which were needed to fill in the memory, right? So that means that we need to send extra 5 symbols, for example, zeros at the end, to actually get this original. But we will not hassle with that. We'll just say that here we are going to use the actual length of where it is, of our uh, received signal. Yes. Well, you know, we so often use this length data Rx that it's beneficial for us to actually evaluate this value here. Length data Rx like new value of n, or let us say better n FLT, right? So here we are going to put n FLT. Here we are going to put n FLT. Here we're also going to put last value of n FLT. And I think there are no more places like that. So let's see. We can actually run this particular script, or let us say better module. Okay, something is missing. Yes, I have missing a bracket. So I have opened this bracket, I have opened this bracket, closed this, but didn't close the sum bracket, right? Okay, let us run. Now it's better. Now you can see that all these zeros that led to intersymbol interference are vanished, right? Still, we have this picture for the same of the 10 signal-to-noise ratio, 10 SNR, for both cases, right? Somewhat worse than this picture. And this line also shows the same thing. Well, we actually might even add a legend as well. So let us add a legend. First is no filter. Second is RRC X1. One filter, only transmitting filter, right? So in this particular case, our signal distorts, or our channel distorts our signal, and we have intersymbol interference And we suffer from that. Because of that, we have greater number of errors. Yes, as you can clearly see here, red line is above. We can also compare, for example, SNR, and P error for without filter, P error with filter. And the number of errors is greater for the second case, yes, when we use one filter. That happens because it still has some intersymbol interference. The intersymbol interference is gone when we have only, how to say it, full raised cosine filter. Now we have square root cosine filter. In order to compensate for that, we need to add second filter. Yes, but right now we can clearly see that it works. It reads data more or less correctly, but does so with more errors because there is partial, not great, but still somewhat partial intersymbol interference. Now we need to add the second filter at the receiver and do the same operations, right? So I'm going to save this as a copy, sim RRC x2, like this, with two filters. Accordingly, say this will be my task 4, relation with two RRC filters, right? This will result be plotted in third picture. Accordingly, I'm going to add an extra legend entry, RRC x2. And all I need to do is to perform filtering once more before before downsampling, I believe. This is correct, right? Let me actually check it fast. SQRTRC. Full RC. So we first add AVGN, then we filter, and then we downsample. That is correct. So that means that before this downsampling procedure, we need to add RRC filtering for receiving part. And it goes the same way. Yes, so again, we calculate data filtered. We don't need to interpolate because it is already interpolated. Yes, so we go straight ahead and perform this filtering for a received signal. So filter, pause, data received. Now, however, each of these filters will introduce this delay. It will be twice as much. Yes. And accordingly, the first value that we are going to read is going to be here a double. Yes. So total filter delay for two filters is going to be twice as much. Well, almost twice as much. This plus one is extra for our real first value, right? So here, pay attention. We need to set this to 2. And other than that, well, we need to replace here for filtering because we are going to downsample this filtered signal furthermore. Other than that, I believe that is it. It should work. Let's see. Something. It is working. So this updated. And the last one, something is wrong here, right? Something isn't working because we should get almost like this result. Also, I can see that I didn't change title. Let me fast do that here. Title x2. And let's see where did I make mistake. So filter delay. wait a minute, I have idea that everything is close to 0, it looks like. Right? So data Rx, data demodulated, right? Oh, wait a minute, data Rx. Well, no, it's actually very large numbers, plus 16 degree. Plus 17 degree. How did that happen? So that means that somewhere here, yes, we have our constellation. It's, well, actually quite a lot of magnifying to do before we get to our constellation. So the values are ridiculously large. Let us find out why did that happen. Well, it was almost easier to manually specify limits, but already we are close, so let's continue. Yes, you can see that now we can see our constellation, and we are far outside of the bounds of this constellation. So something happened with the amplification, most probably, right? So let me double check my example if I did anything correctly. So here we have the same impulse response. Here we have this received signal, filtering. Let us plot this filtered signal, plot dot filtered. Where was that? Oh, real part. Just to find out at what step we get these large numbers. Is that because of noise? Is that because of filtering? Or what? So this filter data is already this large. So let us check then next data that is before filtering. But we cannot because we have overwritten this data, right? Let's say that we will store it somewhere, temp data Rx. Let's run this script again. And let's plot real part of data of temp. So already at this step, it seems to be wrong, right? So yes, it's quite large. And that has happened because of some logical mistake, I'm pretty sure. So filter data here is assigned. Here we okay, we can calculate this data again. We can go step by step. Okay, so let's plot real part of this. A bracket missing. And here is everything fine. You can see that we are in bound of -4 to +4, which is roughly, considering the noise, our levels -3, -1, +1, and +3. So at this step, everything is good. Next step is we are going to add noise, attenuate signal and add noise, obtaining this result. So let us plot. But wait a minute, I need to actually calculate it first. Let us do step by step this code, right? Some small debugging. So let us plot this data Rx, real part. But I can see already that everything is fine. Real part data Rx. Yes, it's fine in the same levels. Okay. Then next step is going to be this filtering. FLT. And it's fine, more or less. Next step is wait a minute. Next step is actually downsampling. Let's try and do that. Not real part of data Rx. Well, this looks more than it should be. We can actually plot data Rx by using blue dots. Yes, and you can clearly see that here we haven't +3, we have 10. And with each iteration, it seems to become more, and more. So something is not really working correctly here. Okay. Let us make more, let us change some variable names, because I fear something is not working correctly. So data interpolated here, data filtered, okay. Then this is going to be data channel. Yes, so this is going to be still data channel. Next, what we have is data filter 2, obtained from data channel. I'm pretty sure we have somewhere confused some variable. It's difficult to find. Okay, what we have here is now data receive, which is obtained from data filter 2. And data Rx is accordingly what we are going to use further. Okay, let us run this code and see how it will work. You know, it seems we are already better. Yes, we no longer have this ridiculous billions size. We still have too large value, and probably that is because we didn't perform some normalizing. Yes, wait a minute. Let's check. Stem hash pulse. So here it is 1. Let us check stem convolution of 2 filters, hash pulse and hash pulse. And here it's not 1, right? Therefore, this is our extra amplification of around 5 point something that produces around 20. 10, 20, right? So we need to normalize with this value. So this normalization can be calculated. Let me double check where did we calculate it in fact in our program. So here normalization. Yes, it can be here seen here. Do you see it? Convolution and then normalizing. This normalizing needs to be introduced here as well during this filtering operation. So where we have filter, here we need to divide with this normalizing. which is maximum of our pulse response. So now if we run this code, let's see how correct are we. So it updated, and as you can see, in fact, pair has, we have improved our result. Yes, you can clearly see that this picture is much better than this. So using these two filters actually produce even better results than using no filter. And we can wait a minute, I think we lost our, yes, we need here PR2 in order to be able to compare them all. So let's run it once more. Why is it so? The question is, how do you think, why is it so? Actually, you need to remember that the spectral density of the noise is infinitely large. The bandwidth of noise, delta F noise, is actually from, well, at least in theory, from minus infinity to plus infinity, right? And our signal bandwidth is somewhat limited around here. So in the first scenario, here, first scenario, right? We didn't have this filter, so all the noise energy in all the bandwidth for noise was affecting our signal, and therefore it suffered more from this noise. In the second case, we did have this filter, so noise wasn't that important in this particular case. Yes, and you can clearly see this from this line, that this line goes down much slower. Although we increase noise, it's still, how to say it, doesn't improve much. Yes, so for example, here you can see that for blue line, we had much greater improvement by improving SNR, yes. And this happened because of the inter-symbol interference of one filter. However, if we use two filters, then we don't have any inter-symbol interference, and we remove this extra noise energy, leading to better results. That's actually one of the reasons why I told you that we need to be very careful when comparing this result with internet. As you can see clearly, this is still quadrature amplitude modulation 16. We don't use any coding to correct any errors, but we have clearly much less errors because we are using filters that cancels noise outside of the bandwidth of our signal, right? So that's the purpose of this practical exercise, to show you how these filters can affect. Yes, well, this in the middle is actually not what we do in practical tasks. We always do these filters, yes, in pairs. So we have transmitter filter, we have receiver filter, and we cannot use any filters also. This has to be these raised cosine filters, yes, with specific parameters. Now, depending on your particular system, these parameters can be changed, yes, but the overall idea is still the same. So I will also try to make some practical guidelines, yes, some additional text information for you to follow during your report preparation. But for now, I hope it will be fine for you to stick just to this video, just to reproduce these results, because I believe this is quite big practical exercise, just as many others will be. But nevertheless, I hope you found it useful or interesting, and maybe this will someday will be like something that you will need to take care in your practical work as well. So, are there any questions?
No, I don't have any questions.
No questions, right? Well, if you will have any questions, then please feel free to write me. And then thank you, and see you next week also here in Teams. And thank you and goodbye.
Thank you.